Inverse functions basically do something, and then the inverse, you can think of it as being something that undoes, I guess. So they do and undo. You actually already know a lot of inverses. We just haven't always used that language to describe them. So for example, a function that adds 3 would have an inverse that subtracts 3. So the inverse function here would just be x minus 3. If we use function notation, we can say that if f of x is x plus 3, then f inverse of x is equal to x minus 3. Notice the notation here. This little -1, it looks like an exponent. It stands for inverse function. And we talk about it a little bit down here. But it isn't truly an exponent. Rather, it's part of the notation. Okay? It's notation used to distinguish an inverse function. And that's how it's read, f inverse of x. If I have a function that multiplies x by 5, then the inverse would divide x by 5. Those are two functions that do and undo. Multiply by 5, divide by 5. Just to practice the inverse notation, we could say that if f of x is 5x, then f inverse of x would be x divided by 5. All right, if I take the square root of x as my function, what's the inverse? What would undo a square root? Well, of course, squaring would do that. So the inverse is going to be x squared. We'll just, once again, write out the notation just for practice. F inverse of x is equal to x squared. Similarly, if my function is x cubed, what would undo the cubing function? Well, the cubed root function would do that. Or, in the vein of the exponential functions we've been thinking about, we could think of the cubed root as the 1/3 power. So, just for a little practice, I'm going to write this one as x to the 1/3, the same thing as the cubed root of x. And once again, we'll just practice the function notation. F of x is x cubed, and therefore f inverse of x is x to the 1/3 power. Just to further investigate these relationships, let's take a little bit closer look at the cubed root, f of x being the cubing function, and f inverse being the cubed root of x, or x to the 1/3. I guess I chose to write it as the cubed root down here. And let's take a look at how the function does something, and then the inverse function will undo that same thing. If I start with an input, x equal 2, the function f of x would make that 2 cubed, or 8. And the function f of x would make the 3 into a 3 cubed, or 27. If I now reverse the process, think of these as my inputs for the inverse function. Notice that when I plug in the 8, the cube root of 8 goes back to 2 again, and the cube root of 27 goes back to 3 again. So quite literally, whatever the function does, we will undo with the inverse function. I'd like to take that a little bit further because it gets at a really important property of inverse functions. If I make a quick table of values for the x cubed function, let's just go ahead and let's plug in 2, 3, 4, and 5. And for x cubed then, 2 cubed would be 8. 3 cubed is 27. 4 cubed is 64. And 5 cubed is 125. Over here, we have the table for the inverse function. And in order to get some nice, easy numbers to work with, it would be nice to use the perfect cubes over here to plug in for the x. So let's just go ahead and use the 8, 27, 64, and 125. So that I can now say the cubed root of 8 is 2. The cubed root of 27 is 3. Cubed root of 64 is 4. And cubed root of 125 is 5. And what I'd like to really call your attention to here is the fact that the relationship between these tables looks like this. The x's for the function are the same as the y's for the inverse function, and vice versa. The y's for the original function are the x's for the inverse function. So our x's and y's have traded places in the tables. And that is very typical of the way that inverse functions act. It goes right along with that do-undo thing, right? So very literally, x and y have changed roles. I could use that fact to go to an unknown function. We have some function f of x, whose equation or formula I have not given you. Instead, I've given you a table of values. For these x values, here are the f of x or y values. I'm now going to ask some questions about both f and f inverse. So, in order to answer those, it might be handy if we just made a real quick table of values for ourselves for the inverse function. Keeping in mind that the x's and the y's trade roles. Instead of x being 2 and y being 5, we'd have x being 5 and y being 2. And continuing on, we'd have 4, 3, and then 2, 4, and then 0, 5, and negative 1, 6. So I've very, very exactly just switched the x's and the y's. That always happens with the inverse function. I can now go ahead and answer these questions pretty easily. If I want f of 4, I go to the function table and say for x equal 4, y would be 2. If I want f inverse of 4, I go to the inverse table and say when x is 4, y is 3. If I want f inverse of 5, go to the inverse table, input of 5, output of 2. And then finally f of 5, I go to the f table, input 5, output 0. Now if you were thinking, gosh, she didn't really even need to write out that inverse table, you're definitely correct. If I just sort of think backwards instead, I could really have answered those questions without my inverse table, right? When I went with f inverse of 4, I could have thought, well, gosh, when I have a function, the input is the x and the output is the y. If I were to use the same table with the inverse, I could have simply thought of that as the y value, 4, and gone back to the x value of 3. So if you prefer not to write out the separate table, it's certainly possible to simply use the given table backwards in order to solve the inverse questions. All right, let's go ahead and look at example 2. Here, instead of a table of values, I've given you a graph of a function, and I've asked us some questions about both the function and the inverse. We'll think about this a couple of different ways, but let me start by just making a little table of x and y values for the function that was given. At this point, X is 0, Y is 1. I also have 1, 2. And I'm not going to try and guess the ones that aren't exact. The next exact point looks like it's over here. 5, 4. And then maybe here. 8, 5. All right. If I wanted to make a table of values for the inverse function, I could certainly do that at this point, just by switching the x's and the y's. So I'm going to do that. There we go. All right. If I want to find f of 1, I can either go to the graph when x is 1 and see that y is 2, or I can go to the table that I made and see the same information. If I'd like to do f inverse of 1, I can either use the original graph and think, well, that 1 is now a y value, so x would be 0. Or I can go to the inverse table I made and say when I input 1, I get y equals 0. F of 5 would be the original. So again, I can go to the graph when x is 5, y is 4. Or I can go to the table when x is 5, y is 4. Looking at f inverse of 5, now I have to think of that 5 on the graph as being a y value. And so I can go here and say when y is 5, x was 8. Or I can also go to the table I made for the inverse. When the input is 5, the output for the inverse is 8. So kind of pick your favorite way here. There's some flexibility in how we think of this. If you work well directly off the graph, that's fine. If it works better for you to make a little table of values, that doesn't take very long, and that certainly works well also. Let's talk a little bit more about this inverse function that we just created a table of values for down here. I'm going to keep this around, but I'm going to go to the next page of my notes here. For the same graph, this is just a repeat of the graph that we had above, I'd like to actually make tables of values, which we did for f and f inverse. But now I'd like to use the tables to graph the inverse function right on these same axes. So I'm going to go ahead and I'm going to use this table of values. And I'm going to plot those points for the inverse function. 1, 0, 2, 1, 4, 5, and 5, 8. If I were to connect those points with a reasonably smooth curve here, it looks something like that, right? Assuming that this graph goes on forever also, of course. And I want to look a little bit more at what we just drew. First of all, in the box down here, in mathematical language, if the point AB is on the graph of the function, then we would reverse that, right? The x's and the y's reverse. So that would mean that the point BA is on the graph of the inverse. Again, the x's and the y's exactly trade roles. The result is a graph that's actually reflections of one another across the diagonal line y equals x. Try and draw that one in here. there's the line y equals x. It's just the diagonal. And notice what I've got here is this black graph and this pink graph are simply mirror images of each other. They're reflections of one another across that diagonal line y equals x. That comes exactly from the fact that the xy's have been reversed when we plotted the points, and it will work for every single inverse function. So if I wanted to go ahead and try that for one that I actually know the equation of, actually I don't. We could probably figure it out from the last chapter. We know this sure looks like a cubic polynomial, doesn't it? But I won't assume that. I'm going to go ahead and say, here's my function g of x. And we're going to try to graph the inverse function. Now I do find that it's easiest to work with at least a few points exactly, and then I can kind of fill it in using the idea of the reflection. So let's go ahead and write down at least a few points that we know for the function that's here. Looks to me like maybe 1, -9 is on that graph. I'm seeing 2, -2. 3, -1. 4, 0. And 5, 7. Those are all pretty good points that are on the original graph. I'll now make a quick table of values for the inverse function, simply by reversing the x's and the y's. There we go. And then let's go ahead and plot these new points, these points that will be on the graph of the inverse function. There we go. And I'm going to be able to just kind of sketch that. But as I do that, let's keep in mind that we're supposed to have the mirror image across this line y equals x, this perfect diagonal. So I'm going to sketch that in as well, just as kind of a guideline. And that way, as I draw, I can kind of use the idea of the mirror image to get the shape right. I'm thinking it'll look something like that. All right. We'll continue in the next video, looking a little bit further at inverse functions.